Okay, so let's compile everything in a single code now. First we started with a polynomial, the polynomial of which we want to find our roots. It was given as x cube minus 13x minus 12. Okay. Second thing was we had to make three guesses. Okay. We had to make three guesses as x0, x1 and x2. Next what we did, we found one root by using the routine, all the 6 steps there. If you look at our code, these are the process. This is the process to find one root. So the initial root that we found. So the routine to find one root, and what do we get from here? We find the root. So let's name it R1. So in step 4, what we do? We reduce the polynomial, divide the polynomial with this polynomial. Okay. We perform deconvolution. Decon. Okay. So after performing that, what we get? We get a new polynomial. So let's name it as initial polynomial. We get a new polynomial P2. Okay, let's just name it P. We get a new polynomial P which has the order n minus 1. It has a order n. Since I am dividing it with this one, I am getting an order less than 1. So if it is 3, I will get order 2. Okay, like this. So I get a new polynomial from this step. Then what you do? Then I come back here and start from the routine again. Okay, I can make new guesses, but I can use the previous guess as well. Same thing. So I make from this step, from this polynomial, I perform the routine again to find. In the second iteration, I find another root. Let's start 2. Then what I do? I again perform deconvolution with respect to this polynomial P1, Pn minus 1, and I get a new polynomial of order n minus 2. Okay, then I repeat the process again. Okay. How long should I repeat the process? As long as the order becomes 1. Once the order becomes 1 means, say for example x plus 3, this is a order 1, so I don't need to perform the routine again. From this equation I automatically know my root is minus 3. Okay, so this process, it can be 3 order or higher order polynomials or like this. So we can if we perform this routine, it is going to return me the output. Okay, so let's take a look at the code here now. So first we start with this portion. Let's just copy everything and in a new code. Okay, so first of all, as you can see here in this step, I have to create new polynomials again and again. So defining every time is not possible for us. So I want to do everything inside a routine, inside a complete routine iteration. Okay, I cannot define again and again. If there is 10 order, I have to define it again and again. So I don't want to do it like this way. I cannot do it manually, so I have to do it automatically. So to do that, I use a different approach. So this is removed. This is also removed. Okay, this is also removed. Let's come here. So what do you do? We define the polynomial in a different way. So the other way of defining a polynomial, that was the matrix representation. It was 1, then 0, then minus 13, then minus 12. So we are going to use this one. This will make it more convenient for us. So let's initialize the polynomial that I want to work with. 1.0, 1, 0, minus 13, minus 12. So this is the polynomial that we want to work with. Okay, then 3 guesses. Okay, let's give it the same guess. Then I don't need this one. I need A, so let's run it. Then this is the routine that we want to check. First we find out the points in our polynomial. So that is, so the initial guesses, these 3 points, we want to identify these 3 points. fx0, fx1 and fx2. Previously we did that using the function, but now we are using this representation. So how you can do that? How you can do the same thing using this representation? So to do that, I need to use another function, a built-in function that is called polynomial evaluation. Polynomial evaluation. What does it do? It takes a polynomial first and the point x, at which I want to find the value of the polynomial. Okay, so this is the p, this is the equation of the p, and these are the points at which I want to find the value. So if we come here, if I make it polyval, polynomial evaluation, the polynomial and the point is x0 at which we want to find the value. Again polyval p comma x1, again polyval p comma x2. So this is my fx0, fx1 and fx2. Then these 4 parameters the same way. Then we find abc. Here one thing you should be careful. This was the original condition that plus is larger or minus was larger. But one thing, if you check here, say a is equals to 2 plus 3i. So this is a complex number. When I take absolute value of a, what I'm going to get? I'm going to get the r, okay, in the other representation. But since we want our method to handle complex value as well, so this check that we are actually defining, it should also have a handle, it should take complex value as well. Okay. If I use absolute value here, then it is not going to take that. So what I have to do, I have to remove that absolute value here. I have to remove it from here. Let's just remove it from here. If I keep it, it will only work for this whole process, will only work for real numbers. But I need the absolute value only for the checking purpose. So let's just put it here. Absolute value of check 1 only for checking, greater than absolute value of check 2. Then check is at this one. Okay. Then I have this r. Then I have this x3, that is our new desired point. Then this a. Okay. Then this new point. Then we iterate this whole process. Okay. Okay. So this portion is done. This portion is done. So next what you do? Okay. After this entire routine is done, the last value that I get, that is x2 actually, this last value, this is our new root. Okay. If you come here, so this process I get this r1 first. Okay. So from this r1 I have to define a new polynomial. If you remember, I have to define a polynomial like this, that is x minus this r, or 1 comma in the polynomial representation 1 minus this r1, sorry, r not r1, 1 minus this r1. Okay, so let's define it here. After this my r1 becomes 1 comma minus x2. This x2 is my new root. Okay, then what we do, we perform, put 3 semicolon here, I don't need it. Okay, so this is my new root. Okay. Then the new p is the deconvolution of my original p comma this r1. So this is the new p. Okay, I get this new p, then I repeat this entire process from this one. Okay, so I need to place another while loop here. While, what was the condition? While the length of my new p is, if you check here, our polynomial should have, so if it is like, if this representation is 1 comma 3, so when it is in this representation 1 comma 3, I don't need to perform this operation again, so it has to be greater than 2. So when the length is greater than 2, I perform this whole process again. I perform this whole process again and end it. Okay, so I think everything is clear, so let's give it a try. Okay, let's give it a try. So as you can see, initially we get 1 comma minus 4, that means minus 4 is one of my root, and the p becomes 143. In the next iteration I get 1 comma 1, that means 1 is one of my root. The new polynomial becomes 1 comma 3, and now since 1 comma 3 this is the length is equals to 2, it does not satisfy the equation, so it breaks out. Okay, so my process is done, but I just need to represent it a bit clearly. So let's define a new value, root is equals to empty. Don't use roots because roots is a built-in function. Don't name your variable same as the built-in function. Okay, so once I define the root, this array is going to actually, we are going to keep all the roots here in this array. So let's, after this step, yes, root is equals to root comma, okay, so root, so the root becomes the x2, that is the last case from this step, that is our root. Okay, so then in the next iteration it will be saved here in this position. Okay, so let's run it again, run this from this portion, let's run the whole thing again. Okay, so as you can see, our root, the final root, after this process we can actually here. So the final root it is showing us 4 and minus 1. 4 and minus 1, that is the 2 root, and the third root was actually this minus 3, this the last polynomial that we get. So actually we can do it like this way, root, the final root should be the root that we get, comma, minus p of 2, like this. Okay, so let's start from here and run the entire process again. Okay, so as you can see, the final root that we get 4, minus 1 and minus 3, and that is our answer. Okay, so I hope the step is clear. Okay, the step is clear to you. Try to do it by yourself. Try to write the code by yourself, step by step, and that is the best approach. Don't just copy it from someone else. Let's check it for another polynomial. Okay, let's just remove this portion, minus, remove the minus. Okay, let's check it again. So as you can see, the final roots are, there is a complex roots, minus 4.43 minus 3.68. I have one real root, that is what should be, and two complex roots, they are conjugate. You can check your answer with the roots of t. Let's roots of 1, 0, 13, 12. You can check it from here. As you can see, this actually matches from what we actually extracted from here, from our code. That means our code is working. You can also increase the 5,8. You can also increase the degree of your polynomial and check it by yourself. So there are 5 roots. As you can see, there are 5 roots and 5 roots. Okay, there is 4 complex roots and 1 real root. You can check it by yourself.